Hi everyone. Here we are to look at another example of a calorimetry problem. We already looked at an example where we took some data where we mixed solutions together and measured temperature and were able to calculate the heat evolved from that and then translate that into a heat of reaction. In this example, however, we're going to be solving for something different. So my question is related to ammonium nitrate, and that is the compound used in cold packs, used to ice injuries. And we can define the thermochemical equation here, NH4NO3, as a solid. When it mixes with water, it dissociates to NH4 plus and NO3 minus ions. And this process has a delta H reaction of positive 26.8 kilojoules. Okay? Now, I just want to remind you of what this means. This is 26.8 kilojoules per 1 mole of NH4NO3, right? It's per mole or per X moles depending on the balanced chemical equation. So if there was a 2 out in front, it'd be per 2 moles of ammonium nitrate, okay? Now, the question asked is here. What is the final temperature of a solution when 24.7 grams of the ammonium nitrate dissolve in 165 grams of water in the calorimeter? The initial temperature is 21.6. Okay? Now, practically speaking, if we want to make a cold pack, if we're a company and we want to design a cold pack, how much material do we need to put into that cold pack such that it cools to a sufficiently low temperature is a reasonable question that you would need to be able to solve for. So this is really connected, I think, to application there. All right, so the first thing that we need to do here is, think about what we're asked to find. We are finding the final temperature, all right? And we know that that's going to be solved through Q is equal to mCs delta T. So we need to know the mass of my solution, which we know, right? That's given. That's 24.7 grams of the ammonium nitrate plus the 165 grams of water, all right? And then we are going to need to know the CS. That's a constant 4.18 joules per gram degrees Celsius. And then delta T, we'll just go ahead and solve for delta T and take care of finding the final temp in a second step, because I find the algebra and the math to be simpler if we just solve for delta T straight away. The only other thing we need to know is the heat. So the heat of reaction here is 26.8 kilojoules per 1 mole of ammonium nitrate. So we need to know how much ammonium nitrate is reacting, because if we don't have 1 mole, we're not going to get this much heat out. If we have more than 1 mole, we're going to get more than that amount of heat out, right? So the first thing I need to do is find moles that are reacting here. So I have 24.7 grams of the ammonium nitrate, and we're going to divide that by the molar mass, which calculates to 80 grams per mole. And so that gives me 0.309 moles of ammonium nitrate. Then I will take my heat of reaction and find how much heat is going to be reacted per 0.309 moles. Should it be more than 26.8 or less than 26.8? It should be less than 26.8 because that's how much if we had 1 mole. We only have 1/3 of a mole about, so it should be almost a little more than 1/3 less. So we're going to find the heat per 0.309 moles. And that's going to be calculated by doing a unit conversion. 0.309 moles, 26.8 kilojoules per 1 mole, and that gives me 8.27 kilojoules. And this is the amount of heat that is absorbed by that chemical reaction in the process of dissolution. And now we have a heat. We are ready to solve for delta T. So Q surroundings, which is what we measure the temperature of, is equal to negative Q of the system. So Q surroundings is going to be equal to minus 8.27 because this positive, the surroundings would be then losing the heat, and therefore the sign is negative. My units for C are in joules per gram Celsius, so I'm going to convert this to joules. So it's 8,270 joules. And we'll plug in here and solve. So the sum total of my masses is 189.7 grams. The CS is 4.18 joules per gram degree Celsius, and delta T is my unknown. I plug in minus 8,270 joules here, and we solve for delta T, which is negative 10.46 degrees Celsius. That should make sense that my temperature is cooling if my reaction is absorbing the heat from the surroundings. So you always want to make sure that you have your signs correct because you can easily make a mistake with the positive or negative sign there. So from that, we know that delta T is equal to TF minus TI, which would be rearranged for TF, delta T plus TI. So I have negative 10.46 degrees Celsius plus my initial temperature, which was 21.6 degrees Celsius. So T final is equal to 11.1 degrees Celsius, right? So we do cool it down to 11 degrees Celsius in the process of dissolving ammonium nitrate. So give some more practice problems a try in the problem sets. Reach out if you have any questions, and thank you for watching.